So the first bit is straightforward, just writing out the oxidation numbers of nitrogen. So remember, oxygen always has an oxidation state of -2, and therefore when you add the sum of the oxidation states together, that will give you the oxidation state of the nitrogen. In this next one, we're working out a half equation. Remember, oxygen always converts to water if there's more oxygen on one side. Balance out your hydrogen atoms by converting them to hydrogen ions. Check your charges. The overall charge on the left hand side is +1, right hand side 0, so we're adding electrons to the more positive side, and now the charges balance out. You can also double check with the oxidation states. We know that NO2- going to NO, the nitrogen has got an oxidation state of +3, it's going down to +2, so it must have gained an electron. Writing half equation for iodide into iodine, don't forget to balance your atoms out. Now before we add the two half equations together for part D, you need to make sure your electrons balance. So we need to times the top equation, everything in the top equation, by 2. So multiplying everything out on the top equation by 2, you then add the two half equations together. So that's half equation A and half equation B. Add the two together, bring them down to get the overall equation. Electrons should never appear in the overall redox equation. So we've got 2 moles of nitrite ions added to 2 moles of iodide ions on the left hand side, bringing down 2 moles of nitrogen monoxide on the right hand side and 2 moles of water, and don't forget your 4 moles of hydrogen ions on the left hand side that I nearly did. And the electrons, as I say, cancel out because there are 2 moles of electrons on both sides. If you so wish, you can check the charges. The overall charge on that side is 0, the overall charge on that side is 0, so the equation is now balanced. In this next question, you're asked to find the role of the nitrite ion. Now nitrite is being reduced, it's going down the ladder, and therefore it means it's taking electrons. It's gaining electrons from the iodide ions. It's stripping electrons, and therefore it's an oxidizing agent. So an oxidizing agent takes electrons, it itself gets reduced. Now we're going to apply our oxidation rules in a titration question. And what we're going to do here, so we know it's a titration, we've got 25 centimetres cubed nitrite. In the burette we have got the 27.4 centimetres cubed of the oxidizing agent, the potassium chlorate 5, for the complete oxidation. So if we draw the pictures we can see what's going on. So what we have to do is to calculate the concentration of the sodium and nitrite, that's NO2 minus, not NO3, NO2 minus, in the flask. We're trying to find the concentration, not in moles per dm cubed this time, but in grams per dm cubed. So what we do in our little storyboard is to fill in the volume and the concentration. So we can see here that the volume of the chlorate ions is 27.4 and the concentration is 0.02. So the next step, you must get the ratio from the balanced equation. This is one step students always miss. Get the ratio of the oxidizing agent to the reducing agent. So it's 2 moles of the chlorate 5 ions to every 5 moles of the nitrite ions. So it's really, really important you get that molar ratio first off. Then what you do is take the essentials out of the question and put them into a table. So the molar concentration, the volume, leave that in centimetres cubed for now, and the amount in moles. So you go to the table, you go to your information and start to put it into the table, lay it out into your table. So we've got 27.4 centimetres cubed of the chlorate 5 ions. We know its molar concentration from the information is 0.02 moles per dm cubed. And for the nitrite ions, we know we took a sample of 25 centimetres cubed. Now immediately from the table it becomes apparent that you can work out the amount or the number of moles of the chlorate ions, because we know that molar concentrate, the number of moles is concentration times volume. We divide it by 1,000 to get it in, because the concentration was in moles per dm cubed. So we're converting our volume here into dm cubed. Now the next thing is moles transfer, and we know the molar ratio. We know there are 5 moles of nitrate to every 2 moles. So there's going to be more of the nitrite to the chlorate. So it's 5/2 times by the number of moles. So we know the ratio, so we simply times the moles of the chlorate by 5/2 to get the correct ratio of nitrite ions. Now in the next step, what we're going to do is take those number of moles and convert it into concentration in grams per dm cubed. So if you're asked to work out in grams per dm cubed, the first thing you're going to need to do is to work out your MR, and this is one step that students always get wrong, so it's worth double checking you've got the correct MR. So that's 1 sodium, 1 nitrogen, 2 oxygens gives you an MR of 69 grams for every mole. So we now know that the mass, because we're trying to find the concentration in grams per dm cubed, we know we can now convert that to mass. So that's the number of moles here times by the MR. And that is in 25 centimetres cubed. So that would give us the number of grams that were in our 25 centimetre cube sample. But we're asked to find the number of the grams in 1 litre in 1 dm cubed. So all we do is say, well, how many times bigger is 1 dm cubed? So there's 1 dm cubed, 1,000 centimetres cubed. It's 40 times greater. So if there are that many grams in 25 centimetres cubed, you times all of that number by 40, and your answer comes out to 3.78 grams per decimetre cubed. So again we have a simple working out a redox equation, looking at two half equations. The first thing we do is to need to balance up the number of electrons. So you can see here that this is giving up 2 electrons, the reducing agent is giving up 2 electrons. We need to times it by 3 so that the oxidizing agent takes 6 and the reducing agent takes 6. So times the whole half equation by 3. Bring down the reactants, that's 6 moles of S2O32 minus, and the oxidizing agents, that's 1 mole of that, so we tick that off, that's gone, and 6 moles of hydrogen ions. But over this side we've got 3 moles of S4062 minus, bring that down, add together 1 mole of bromide ions, bring that down, and also 3 moles of H2O. We can cancel the electrons out because there are 6 electrons on both sides, so in your overall redox equation you never have any electrons. Make sure your electrons have disappeared. We can now check that this equation works because we can now balance the charges. So on this side we've got 6 times minus 2, which is minus 12. This is charge and oxidation state, plus an overall minus 1 plus 6. And on this side 3 times 2 minus is minus 6, minus 1 from the bromide ion here. So the overall charge on this side is minus 7, and the overall charge on this side is minus 7, so your equations are balanced. Like the other example, this redox titration is best storyboarded. So first of all, take the essential information from the question and put it into a quick sketch of the titration apparatus. So it's really important you don't get the concentrations of the 2 reagents mixed up and you get the names correct. So thiosulfate from the last part of the question was S2O32 minus, and the bromate 5 is BrO3 minus. The concentration of the bromate is not 1 times 10 to the minus 3, but 5 times 10 to the minus 3. So we change that to 5. It's really important that you get the correct information from the stem of the question. So once we've filled in the storyboard with the correct concentrations and the correct volumes, and just again checking the concentrations, we're asked to find the expected titer. The titer is the volume of the bromate 5 that's coming out of your burette. So what we're now going to do is we're going to find the ratio of the oxidizing agent to reducing agent from the balanced equation we had on the previous part of the question. And what we can see here is that 6 moles of the S2O3, the thiosulfate, so that's the sodium thiosulfate, we leave out the sodium because it's spectator ion, to every 1 mole of the sodium bromate 5. Again, we leave out the sodium because it's spectator ion. Put all of your information into a table, because by laying it out this way, you'll be less confused as to what you've got to do next. So we've got the molar concentration of the bromate, which is 5 times 10 to the minus 3 moles per dm cubed. We've got the concentration of the thiosulfate, which is 1 times 10 to the minus 3 moles per dm cubed from the question. The volume of the thiosulfate is in the conical flask, which is 25 centimetres cubed. And therefore the amount is concentration times volume, which then can be transferred to the moles of bromate. But because it's a ratio of 6 to 1, we times the number of moles by 1/6. We reduce it down to 1/6 of the number of moles. So now we have the number of moles of bromate in our titer that was in the burette. We need to find out what the volume is. So the top number of moles, which is tiny, coming out of the burette is 4.17 times 10 to the minus 6 moles. Now the next step, therefore, is to find the volume or the titer of the bromate coming out of the burette. So remember, the word titer means volume. So we now rearrange our equation, and we know that to get the volume, you need to divide the number of moles, the amount, by the molar concentration. The number of moles we've just got from the first part of the question, which is 4.17 times 10 to the minus 6 moles in that titer, divided by the molar concentration, which is 5 times 10 to the minus 3. Now this gives us a really small number, but remember that's in decimeters cubed. We times it by 1,000, that tells us we've used 0.83 centimeters cubed from the burette, which is really, really small titer. And that's not much use. That will reduce your accuracy. So if we want to improve our experiment, to improve the accuracy for the concentration of sodium thiosulfate, we need to increase the volume. How would we increase the titer volume? Well, if we reduce the concentration, if we make that number smaller, it's going to make the volume larger. So we need to reduce the concentration of the bromate 5. The value of V increases, because in an error calculation, it's the apparatus uncertainty divided by your reading. So the uncertainty of the apparatus, which in this case would be a burette, divided by the measurement. So to reduce the error and increase the accuracy, you need to increase the measurement. So you would use a larger volume. So in effect, decreasing the concentration of the bromate would increase your volume, your error decreases. There's your answer.